Hi everyone. So welcome back. So we were talking about activation functions, and we looked at a few popular ones, starting with the logistic function, then the tanh function, then the relu, and a few of its parameters like the leaky relu, the parametric relu, and then the exponential linear unit, right? And in all of these cases, we made some comments about how do the gradients behave, and then what can we do to how these activation functions evolved to take care of certain drawbacks of the earlier activation functions, right? So tanh was preferred because sigmoid had certain problems. It was not zero-centered. So movements only in few directions were possible. Then relu is better than tanh and sigmoid because it's simple to compute and it does not saturate in the positive region. Then the variants of relu are better because they allow some gradients to flow even when in the negative region, right? And so on. So we did all that. And now we'll continue our journey on more activation functions. We'll do around 3 to 4 more, starting with the Maxout activation function, right? So we'll motivate that, starting with dropout, and then try to connect it to how there is some kind of, I wouldn't say relationship, but some analogy that you could draw from dropout. Okay. So we had discussed about this model averaging, where you have a data set and you create sub data sets from there by sampling with replacement. What do I mean by that? So I have, say, 1,000 data points. Okay. I want to create another data set of 1,000 data points. How I will do that is I'll pick one training example from the original data set, put it in this bucket, right? And then keep the training example here also. It's not being removed. So it's not that now you have 999 samples here. You have the entire 1,000 samples. I took one from there, sampled randomly one from there, created a copy and put it in this bucket. And I still have 1,000 here. Again, I sample one randomly and put it in this bucket. And I keep doing this till this bucket has 1,000 entries, right? So I'm sampling with replacement, and I'm creating multiple such multiple such training sets from the original training set. And each of these training sets will then be used to train a model, and those models would have their own parameters like W1 to WK. So here W, just think of it as theta, right? It's a collection of all the parameters in the models. I'm calling it W here, all the parameters in the model. And here W1, W2 correspond to the parameters of these k different models, each trained on a different version of the training set. And each training set has the same size, but it contains sampling with replacement, right? So what would happen in that case is that it is shown that if you do this sampling with replacement, right? So this bucket that you had, the first bucket that you created, that was used to train the model f hat 1x, which had a collection of parameters w1. So that bucket, around 46% of the samples there would be duplicate. And it does make sense, right? Because you're sampling with replacement. So roughly half the samples would get duplicated in this set. So it won't be that all these 1,000 would be unique. That should be obvious. And there's also some analysis that roughly half of the samples are actually duplicates. So we always expected duplicates. There's a study which says exactly how many duplicates you can expect, right? So now you have 1,000 data points, but there are duplicates in that. So now the model has a better chance on overfitting on that, right? Because now you have fewer samples than the original training data, and you're seeing the same samples again and again. So the model gets a chance to adjust on the same sample more times now, right? And hence in these models, each of these models, F1 hat to F2 hat, would like really better overfit to the bucket of training data on which it was trained, because that bucket is containing duplicates and each model is seeing the same training examples multiple times. And then when you do inference, you do some kind of model averaging. It could be arithmetic mean or geometric mean. Any of these are possible that we have seen. Right? So we take the prediction from all the k models, and then we take the average is one possibility, or you could take the max, that is another possibility. You could even take voting. All of those possibilities exist. Right? So this is what happens in model averaging. And then in deep neural networks, the way we had done that was using dropout, right? So we had we knew that it's difficult to train multiple models, so dropout was our substitute for getting the effect of model averaging. Okay. Now The same thing I'll just repeat, right? So the model weights get optimized for a specific set of sample, each of those buckets corresponding to one of the models. The model is overtrained on that bucket, so it overfits. But in dropouts, we don't have a similar luxury, right? So in dropouts, what is happening is that you have these multiple submodels. Each submodel is getting sampled rarely, right? Because there are an exponentially high number of submodels. So each submodel is getting sampled rarely. So each submodel is not getting the chance to overfit on specific portions of the data, because hardly it will see the data once. I mean, forget about seeing it twice, it may not even see it once, right? So this kind of phenomenon which happens in model averaging or in bagging, where each submodel or each different model gets a chance to overfit on the training data, dropout does not really get that chance, right? So now in the case of bagging, the model is getting to update the weights again and again on the same training sample. But in the case of dropout, it's not getting that chance. So whenever it sees a sample, we should try to do a larger update, right? Because if this data point is sensitive, we should try to do a larger update. But then how do you do a larger update? Maybe you could increase the learning rate. But if you do that, there could be problems, right? We have seen several problems with increasing learning rate. And in the case of dropout, since these parameters are shared across all these submodels, now you increase the learning rate, it could have effects on the other submodels, right? So that's the situation where we are in. We motivated dropouts from model averaging, but now we are observing that something which happens in model averaging, where every submodel gets to overfit on the specific training data, that effect does not really happen in dropout. And in dropout, still we do model averaging, right? So now the way of model averaging was again that each of these neurons, you consider their output and you multiply it by a fraction p, which is the number of times this neuron was on, right? So we are just assuming that all neurons were equally participating and equally sensitive to all the training examples, and hence they were all on only a fraction of times p. So we'll take all of their weight as p, assign a weight p to all of them, and then do the model averaging, right? But this gap is still not being addressed, that in bagging actually the model overfits on specific samples, whereas in dropout the concept of overfitting is not really happening on any specific training examples, because each submodel is rarely seeing the training data, right? So now how do we close this gap? Can we do something? So that's where Maxout gets motivated from. So this is what dropout does, right? So dropout, at every time step, now you have 4 neurons in the hidden layer, H11, H12, H13, H14. So you'll apply a mask, right, with probability P. So some of these would be on, some of these would be off. The ones which are off will not participate in the computation. So in particular, if I am computing A21, only H11 and H14 will participate with the corresponding weights W11 and W14. If I am computing A22, then again only H11 and H14 will participate with the corresponding weights W21 and W24, right? And now what would happen? Yeah, so now let's consider a scenario, right, where these two outputs, A21, A22, have the following relationship. They're both greater than 0, because I'm taking them greater than 0 because it's a relu activation function, so I want both of them to be active and not dead. So say both of them are greater than 0, but A21 is less than A22, right? So what does that actually mean? Let's try to understand that in terms of how neurons react to training samples, right? So if A21 is actually less than A22, it means that A22 is reacting more positively to this training sample, right? It's firing for this training sample even better because its output is high, right? So now if you relate it to our earlier discussions on MP neurons and so on, we had the situation that if the inputs are of a certain configuration, then this neuron fires, right? Now this neuron is firing more than this neuron which is firing weakly, right? So now that means this neuron is more sensitive to this training data, and maybe I should respect that, right? So when I am updating, can I update this better as opposed to updating this, right? Because this is reacting weakly, right? So can I do that? So one option of doing that is to take the, yeah, so this is the effect that we want, right? That we want to make these, we want to acknowledge the fact that these neurons are sensitive to certain training samples. One neuron is more sensitive than the other, and hence I should perhaps try to get this effect which I had in bagging, where the neurons were adapting to the specific bucket of training data. And now since this neuron has shown some preference for this training data, can I give it more preference? Can I make its updates better? So as opposed to the relative updates of the other neuron, right? I don't want that other neuron to specialize for this training sample because it has not shown interest in this training sample, right? So one way of doing that is, now I could take the max of these two. So max would turn out to be A22, right? And then when the gradients flow back, right? So now what is H21? It's the max of A22 and A21, which is equal to A22, right? So now if I take the derivative of H21 with respect to A21 and the derivative of H21 with respect to A22, then this would be 0 and this would be 1. So the gradient will only flow to this part, it will not flow to this part, right? And that's what you wanted to achieve, that you wanted to make this neuron specialized by giving it the signal and ignore this neuron because it was not really showing much enthusiasm for this input. So let it not fire, and I'll kind of ignore it and just try to make this other neuron specialize on this training sample. And if you do that, then in some sense your different neurons are kind of getting adapted to specific training samples, and you're getting the same effect as you expect in model averaging or in bagging, right, where certain neurons are, certain submodels are specializing for certain training samples, right? So that's the effect that you're trying to achieve, and hence you do this max. Now what was A21? A21 was actually this, and A22 was this. So you can think of these as there are two linear transformations happening here, and you're selecting the max of those linear transformations. And why restrict at 2, right? So you could even have k linear transformations, and you could select the max from that, right? So let's just delve a bit more into this over the next few slides to get this picture clear of what I mean by k linear transformations, right? So this is what happens in Dropout, right? We're still trying to compare Dropout and see what was happening there. So in Dropout, what happens is I can divide this nodes in this hidden layer, right? This was the hidden layer. I am dividing the nodes into 3 parts. One is the black nodes which have been dropped out, so they are completely not participating in the output, right? They are not participating in the computation at all. And then there are 2 types of nodes. One are strongly responding nodes, and the others are weakly responding nodes. And now in the case of Dropout, irrespective of whether you are strongly responding or weakly responding, the gradients do flow back to you, right? And the gradients will of course flow back in proportion, but you're still, all of you are being responsible for the output, and the certain nodes may not maybe get spatialized for the specific input, right? So that's what is happening in the case of Dropout. Now if you look at the submodel that we have in the case of Maxout, what is happening here is the following, right? So this is what is happening in Maxout. Now I have considered Maxout layer, and because I can't show many neurons here, this is one Maxout neuron, okay? This Maxout neuron in turn has 3 nodes. Each of this has some linear transformation, right? So this is W1 transpose X, this is W2 transpose X, this is W3 transpose X, and then I'm only taking the max of these guys and allowing it to pass forward, right? So in essence, these 2 nodes have been dropped out because of the max operation, so you are getting the same effect as Dropout. Similarly, you have these 2 nodes here, this Maxout neuron here, which has inside 3 linear transformations happening, okay? Let me just call them as W1, maybe call it W tilde transpose X, W2 tilde transpose X, and W3 tilde transpose X. See here again I had 3 linear transformations, then I just selected the max of those and dropped out these neurons, right? So now as opposed to Dropout, where after dropping out, all the neurons participate, and even during inference we take equal weightage to all the participating neurons. Now we are ensuring that the neurons which participate, only the strongest ones of those are actually active, and we are further dropping out the weak ones. Okay, so this is what max out looks like. So you have max of multiple affine transformations. I've been saying linear, but they would be affine because there's a plus b also possible there, right? Yeah, so these are the multiple affine transformations inside. I have shown n of those, and then you're just selecting the max of those two, right? And you could even think of max out as a generalization of the relu function, right? So now you could think of a relu function, any of the relu functions, right? Relu or leaky relu or parametric relu, as a generalization of or as a special case of the max out neuron, such that there are two neurons inside the max out neuron, and for one of them the weight and the bias is 0, and then for the other one you have W2 x plus b. Now in the case of relu, now W2 is again just equal to 1 and b is equal to 0. So then you're just left with max of this quantity is 0 and the other quantity is just x, right? Now in the case of the earlier leaky relu that we had seen, this was 0.1 x. So you could think of it as again max of 0, comma 0.1 x plus the bias again is 0, right? So this is also a special case of the max out neuron. So you can think of max out neuron as generalizing relu and all its variants. And again, it gives you more power, more non-linearity. So this is what, if you have these two max out neurons, right? So if one of them learns the value of W1 as 0.5x and the other one learns the value of W2 as minus 0.5x, then effectively you are getting this V-shaped non-linearity, right? Which is the same as the absolute function. And then you can also show there are certain configurations possible. So suppose you have 4 affine transformations within a max out neuron, right? So I'm talking about a max out neuron. This is what a max out neuron looks like. It has 4 affine transformations, and I'm going to take the max of those, right? And if those affine transformations happen to be these are the 4 affine transformations. Then if I take the max of this, then I almost can approximate the x square function, right? So it's giving me a higher degree of non-linearity. And of course, it has the other benefits. There is no saturation, no depth now, because it will flow through the max path. And the max, at least one of the neurons would be great. As long as it is greater than 0, you would have some gradients flowing. And for multiple affine transformations, the more you have, there is a proportional increase in the number of parameters. You could think of that as a disadvantage. But there is a proof which also shows that 2 max out neurons with sufficient number of affine transformations, right? So you just have 2 of these, but you have a large number of affine transformations inside them, right? Then these can act as a universal approximate. So you just need like 2 max out neurons to approximate any function. So that's a kind of a testimony for the non-linearity or the representation power that max out neurons brings in. Of course, max out neurons, despite whatever I have explained, are still not very popular. I think their special case, which is relu or any of its variants, they are still more popular. But it's good to know about them. It's good to see the analogy with dropout. It's also good to see how they generalize relu and other functions. It's also good to know that just 2 max out neurons are can act as a universal approximator, right? So this all helps you build a better understanding of some of the concepts in deep learning, right? So that's all I had to say about the max out neuron. I'll end this video here, and then I'll come back and talk about some other activation functions.